Well, hello there, all you cool cats and kittens. What I'd like to do right now is clarify some important ideas that will help you for your upcoming mechanical energy test. First, let's clarify the definition for energy. We said it's the ability to cause a change to happen. If work is achieved, that's an example of a change. I want you to keep in mind, however, the change is not always a good or productive thing. It could actually be a negative change. For example, in a collision, an auto collision, the damage that occurs is the change or the work accomplished, but we don't consider that to be a very pleasant thing, right? The more energy something has, the more change it can cause, or the more work it can accomplish. The symbol for energy is a capital E. So one of the things that I want you to remember is that energy is unique and distinct. It is not the same thing as force, power, and work, or even momentum and acceleration. Those words students tend to use interchangeably with energy, and they are not the same thing. So you do not need to know the formulas for work or power because you learned them back in 6th grade. I want to remind you that what you see on the screen is basically proof that force and power and work are not forms or types of energy, but they are calculations that can help us quantify energy or put a number value to energy itself. Now, forces, remember, is a push or a pull. Forces are not energy. So gravity is a force, right? That means gravity is not energy. Friction is a force. That means friction is not energy. So when we think of friction, right, we think about maybe rubber tires on a road as a car skids to a stop, or maybe an eraser that rubs on a piece of paper when you erase something. That's friction. We usually, heat is a byproduct, thermal energy is a byproduct of that, but the actual friction itself is not energy. Air friction is another example of friction, and that's the resistance you feel if you're maybe on your bike and you feel the wind blowing through your hair, or when it's a really windy day, you get that resistance from the air, and it's making you have to pedal harder. That's considered air friction. So air friction is just an example of friction. But the big thing you need to know, again, you do not need to know the formulas for work or power. You just need to realize that work, force, and power, and including momentum and acceleration, these are words that students use mistakenly to say that it's the same thing as energy, and they are not the same thing. Forces greatly influence and affect energy, and power and work and acceleration and momentum are all equations. And we can use those equations to describe motion, and we can use those equations to describe how much or how little energy something has, but they themselves are not energy. All right, so one of the things that we did before we did the crash lab is I asked you to watch some videos on what is energy, and you had a video lesson with my voice going over what energy is, which was a review of the first 3 slides that we just did. And I just want to recap. There are 6 types of energy that you see in yellow. Remember that we talked about the fact that because of the fact that we're in remote learning and also the shortened year, electricity, hopefully we'll get to at the end of the year, but we may not. Nuclear energy is safe for when you're in high school. But what you see in yellow are the 6 different types of energy. What you need to realize is that mechanical energy includes kinetic and potential combined together. In fact, the definition for mechanical energy is the sum of all potential and kinetic energy in the system added together. We are in the mechanical energy unit right now. Thermal energy is also known as heat, sound energy, electromagnetic energy. So most people think light, right? Light is a form of energy. Well, light is actually a subcategory of electromagnetic energy. Again, this is something that you learned in your previous video lesson of what is energy 2 weeks ago. But there are 7 subcategories of electromagnetic energy. So if I gave you a list of different different things on the test, and I say circle everything that is an example of energy, if it's from this list, then you would circle it as an example of energy. If it is not on this list, it is not an example of energy. So for example, momentum, power, work, force, gravity, friction, those are power. Those are all non-examples of energy. Okay, so let's look at kinetic energy and gravitational potential energy. Look at it a little bit more closely. So kinetic energy is the energy of something that's moving, right? The object that's moving. However, I don't want you to just think about a ball flying in the air, right? Or maybe water flowing in a river, or a car going down the road. Those are all things that your eyes can physically see in motion. But there are a lot of things in motion that our eyes cannot see. Wind, for example. The evidence that it exists is that we can feel the breeze, right? But then there's a lot of motion. In fact, this is where sound and heat or thermal energy is going to come into play later on in the school year. But there's a lot of motion at the molecular level where molecules are actually moving or vibrating, and that's considered kinetic energy. So don't just think what your eyes can see that are moving, but also think about those things that are moving that we don't see. Potential energy is stored energy, right? Well, there are 3 types of potential energy. There's actually 5, but in 8th grade, we focus on 3. Gravitational potential energy, you should be familiar with that after today's lesson. Elastic potential energy, that's usually like if you stretch a rubber band, that tension you feel, that's elastic potential energy stored within that rubber band. If you push down on a spring, you feel that tension. And again, that's elastic potential energy. A bow and arrow, if you pull the string back, that tension you feel is an example of elastic potential energy. Chemical potential energy. So for example, gasoline, or it's called petrol. If you put it inside the tank of a car, it would have to go through a process to transform or convert from stored chemical energy to most likely kinetic, to make the cylinders in the engine of the car pump up and down, and to make the car move, and to make the tires turn so that the car can move on the road. A log, for example, has a lot of a log has a lot of chemical potential energy stored within it. I can prove that to you because if we light it on fire, it goes through a chemical change. It transforms from stored chemical potential energy into thermal energy and light, right? Because the fire creates light. Food is the best example of chemical potential energy. So we eat a pizza, and then 3 days later, we have the ability to run 6 miles or to jog in a soccer game. And that's because our body metabolizes or breaks down the chemical potential energy stored in our fat cells from the food that we previously ate so that we can move. So this is all the examples of stored energy. The ones that we're focusing on in the crash lab and right now in our mechanical energy theme is gravitational potential energy. So this is stored energy. But what I want you to realize is that usually the object's not moving, but moving objects can also have stored energy in it simply because of their position on Earth. Because everything on Earth, as you know, is affected by gravity. So what we want to basically say about GPE is that when the object is not moving, or maybe even if it is moving, it still has energy always stored within it, simply because it's always being affected by gravity. And when it finally goes into motion, like for example, when it falls, that's when it has the opportunity to finally express that energy that was stored in it all along, stored potential energy. So we already learned from the crash lab, there are two factors or variables that influence or affect kinetic energy, and that is how fast or how slow the object is going, and how heavy or how light the object is. So speed and mass are the two variables that affect kinetic energy. So if an object has a lot of speed and a lot of mass, it's going to have more kinetic energy. If it has less, if it's slower and it's lighter, it will have less kinetic energy. Gravitational potential energy is based on how high or low it is, and of course, how heavy or light it is. So mass and height are the two factors that affect GPE and KE. Here are the formulas for actually calculating the kinetic energy of a moving object and the gravitational potential energy that is stored within an object. Usually it's non-moving, but it can also be moving. So here is the formula. Long ways it's written for kinetic energy equals 1/2 mass times velocity squared. Velocity is a synonym for speed. But watch carefully. It's not mass times velocity and you take that product and you put it to the second power and square it. It's only the speed that you multiply by itself, and mass is only used once in the equation. So you have to remember the order of operations. Please excuse my dear Aunt Sally, right? Parentheses first. Excuse E is exponents. So anything that's in exponents you take care of first. So you're going to actually multiply the speed by itself, get that product, hit equals on your computer, and then take the mass of the object, multiply that, and then divide the whole thing by 2. Or you can multiply the whole thing by 0.5, right? Because 0.5 and 1/2 are the same thing. So M stands for mass, V stands for velocity or speed. Now, units. When I say unit of measurement, that should sound familiar to you. Unit of measurement means, like, if I'm measuring temperature, the unit of measurement would be degrees Celsius or degrees Fahrenheit or even Kelvin. If I'm measuring time, the unit of measurement for time could be minutes, months, hours, days, seconds. If I am measuring the volume of a liquid, I can measure it in ounces, or I can measure it in liters or milliliters. Mass or weight can be measured in grams or kilograms. The unit for energy, whether it's KE or GPE, or whether it's thermal energy later on in the year, or light energy, we're going to focus on the unit of joules, Joules. The abbreviation is a capital J. So how do you calculate, how do you put a number value to how much or how little GPE an object has stored within it? And that is from the formula. Here it is written long ways. The mass of the object times the pull of gravity on Earth times height. Also known as mgh. M, mass, times g, the force of gravity, times height, how high that object is off the ground at the moment you are watching it. So the pull of gravity on Earth is always 9.8 meters per second squared. Let me reference that. 9.8 meters is basically take 10 meter sticks and line them up. Line them up from the floor all the way up top. So line them up vertically on top of each other. So think of 10 meter sticks piled on top of each other. The pull of gravity on Earth is strong enough that it would pull you down in 1 second the distance of 10 meter sticks, just to put it into relation. 9.8 is the number that you will always, it's like a constant value or variable that always gets plugged in for the G value. 9.8 will always be provided on the test. You do not have to memorize that value. Okay, so can you transfer kinetic energy from one object to the next? Yes. So a football player tackling another football player would be a perfect example of a transfer of kinetic energy. A swinging bat that hits a baseball, that would be an example of a transfer of kinetic energy. Can you transfer GPE? No, because usually the object is not moving, and that is energy stored within the object that even when contact is made, that object will keep that energy stored within it and not transfer it out to something else. Okay, so here's some examples of GPE versus KE. Obviously in our lab, when the car was parked, it had GPE, but when it was actually rolling down the ramp, or when the parked car was sliding across the table, that would be kinetic. Water that is stored behind a dam is not moving yet, so it has the potential to fall through to a lower elevation in the river, but right now it's being held up by the wall of the dam, and therefore it's that water is basically considered stored potential energy, or it has GPE. As soon as you open the gate, the water will start flowing because it falls down and it will flow down the river. At that point, the water is now in motion, so it has kinetic energy. All right, describe the kinetic energy and the gravitational potential energy, which the abbreviations are KE and GPE at each position. So if you've ever watched the cartoon, The Roadrunner, he takes off, meet, meet, pew, and he takes off, and there's a dust trail behind him, right? Well, physicists love to make diagrams with dust trails to show that that object is in motion, it's moving. What's the difference between this and this? What do you think the artist of the diagram is trying to communicate? Hopefully you said that the ball at position B is moving faster, at a faster speed than the ball rolling at position C. You're assuming that this is the same ball, it's the same mass of the ball, it's just, let's look at the ball, let's kind of like freeze frame it in different positions as it starts at position A at rest. The person lets go of the ball and it rolls down the ramp and across the racetrack. Well, let's freeze frame it and let's study the energy of the ball while the ball operator is holding the ball. Notice how the ball is at the highest elevation at position A. It's not moving yet, so it is 100% GPE. The energy expressed in the ball right now is 100% GPE. We would also say that the ball has maximum GPE at this point because in this whole ramp system, the ball at position A is at the highest point, okay? If I switched this ball, right now it's hollow, right? What if I put it with a same size ball, but it was solid, so it was more massive? It would have more GPE at rest because mass and height affect how much or how little GPE a non-moving object has. Okay, so obviously if the ball starts to roll down the ramp, you should know at this point, just from practical experience of you coasting on a bike down a hill or sledding down a hill after it snows, you know that you're going to be at the fastest speed at the bottom of the hill. And we've already talked about why. It's because that object has this much time, all of this time, to build up speed, to be exposed to the force of gravity and have the opportunity to build up more and more speed. So no matter how steep or how gradual the hill is, if any object is rolling down a hill naturally because of the force of gravity, it will be at the maximum speed at the bottom of the hill. So if it's at maximum speed, it's going to be at maximum KE, because remember, mass and speed affect how much or how little KE a moving object has. If it's the same ball, mass does not matter because it's the same object, but its speed does. So we would say that the ball has maximum GPE at position A, and it's not expressing any kinetic energy right now at position A because it's not moving. At position B, it has a lot, maximum amount of kinetic energy, but it has minimal amount of GPE because it's at the lowest level. So B and C are level with each other. They're at the lowest point of this whole system. So that's at positions B and C, the ball is going to have the lowest amount of GPE because it's at the lowest position or the lowest height. Now, why does the ball slow down? I hope you said friction, right? So even on the level surface, eventually this ball is at maximum speed at the bottom of the ramp, but eventually on this level surface, it's going to slow down due to the force of friction. That's why we have only 2 dust trails versus the 3. The artist is trying to show you that the ball is moving slower at position C. It's still moving, so it has KE. So we would say that the ball at position C has less kinetic energy than the ball does at position B. So do you see how I described? I compared and I contrasted the kinetic energy and the gravitational potential energy of the ball in different locations within this ramp system. So when you look at this, you should be able to describe for me the amount of kinetic energy that the ball has at different positions on this ramp. And you'll have an opportunity to do that at homework tonight and the rest of this week. Okay. Remember I told you that momentum is not energy, and neither is acceleration, and that's because they have their own calculations also, and they are not the same thing as energy. So momentum has a formula very similar to kinetic energy, but it's a little bit different. So it's mass times velocity, but remember that the equation for kinetic energy is 1/2 mv squared. So again, I'm proving to you with the formulas that mass and energy are different things. Momentum and acceleration are not examples of energy. Okay, so I hope you found this lesson helpful. It clarifies the vocabulary that you need to know, as well as the formulas you need to know for the mechanical energy test that is coming up in a little bit over than a week. All right, see you later, everyone.